So let's think about what's actually going on during this process. We have a fin that starts from equilibrium, and then as you add heat, it's got to do sort of two things, right? It's got to equilibrate externally with its surroundings, so that takes a certain amount of time, and then it's also got to equilibrate internally. So let's see if I can find these calculations, and that takes a little bit of time, right? So the external equilibration is basically how long does it take the material in the fin to rise to its final level where it's in equilibrium with its surroundings. And then the internal equilibration is how long does it take conduction to go from the base to the tip so that the fin can have its final shape, right? And we know how to calculate these two different time constants. The external time constant is the resistance from the surface to the surroundings times the capacitance, which I've calculated here using a resistance that's only related to convection. I get 24 seconds. So it's going to take about 24 seconds for my fin to come to equilibrium relative to the surroundings. And then it's going to take about L squared over 4 alpha, right? This is my internal time constant, which is 36 seconds for this problem. It's going to take about that long for the thermal wave to move from the base to the tip, right? So both these processes have about the same order of magnitude time. And I know then that if I simulate 50, 60 seconds, everything should pretty much be done, and that's exactly what I saw here in my solution. Right? I simulated 50 seconds, and when I ran this, which I keep losing my plot somewhere, when I ran this, at the end of my 50 seconds, you can see things were pretty much done. So we can start to think about what this might look like if we changed some of the parameters in the problem, right? So, for example, we could think about what if we reduce the heat transfer coefficient by a factor of 10, right? So if I look at these two equations, reducing the heat transfer coefficient is not going to take how long the internal equilibration process requires, right? The thermal wave is still going to move from the base to the tip over about 36 seconds, but it is going to change how long it takes to come to equilibrium with the surroundings, and that's going to take now, instead of 24 seconds, about 240 seconds, right? So this is going to take a lot longer to come to equilibrium with the surroundings. The other thing I know is that if I make our convection a lot bigger and I keep our conduction the same, my fin is going to be a lot more isothermal, right? It's going to be a lot more isothermal, a lot less temperature drop due to the conduction along the fin, right? So I can make that change here. I'll go in here and instead of having this be 50, we'll divide that by 10. I know that I better simulate a lot longer, so let's simulate maybe 250 seconds instead of just 25 seconds. And I'm going to expect that because I'm making the resistance bigger, the temperature rise is going to be somewhat larger too. And what I would expect to see now is that the fin comes to its final equilibrium shape pretty quickly, because that's a conduction process, right? But then it takes kind of a long time for that shape to rise up relative to the surroundings. So I will go in here and reduce the heat transfer coefficient by a factor of 10. I better simulate kind of a longer time, so maybe 250 seconds. And if I reduce the heat transfer coefficient, I think it's going to get a lot hotter, so maybe we should make this 620 Kelvin. And then we'll run, and you can see that, yeah, in fact, it comes to a steady state shape pretty quickly, and then it takes a long time for that shape to just slowly rise up towards its final sort of resting place here. So that obeys our intuition of what should be happening. I guess the last thing we could do is think about what would happen if we reduce the conductivity, right? So if we reduce the conductivity but keep the heat transfer coefficient where it was, then my external time constant is still 24 seconds. But now my internal time constant is going to get a lot bigger, right? So it's going to take a lot longer for that thermal wave to move from the base to the tip, and in fact that's ought to be what sort of dominates the whole process, right? And we should also expect that because that conduction resistance is so high, my fin is going to get it's going to have a very large temperature drop along it due to conduction. So let's see if we can actually observe that kind of a process. So I'll put this back to where it was. I will reduce the conductivity by a factor of 10. I better still simulate kind of a long time, maybe even longer, so 350 seconds, and that might be about right. So let's see what this looks like. So yeah, sure enough, you can see that thermal wave taking kind of a long time to move through the material, which is what you expect. And you also see a large temperature gradient along the fin, even though. And that's due to the large conduction resistance that you have going on. All right, so that's interesting. I guess the other implicit technique that we ought to talk about is one that's probably a little bit more useful, and that's called the Crank-Nicholson technique. So the fully implicit technique is a first order technique, right? We only evaluated the temperature time once, and we did it at the end of the time step. Crank-Nicholson is implicit, but it's second order. And it's second order because we're going to evaluate the temperature time twice. Once at the beginning and then once at the end. And so again, it will be implicit in that all of these equations will have temperatures we don't know in them. But we solve it the same way, right? Here's that written out for this problem, right? You can see I have an evaluation of the temperature time at the beginning and then another one at the end, and each one of those is weighted equally. And then if I want to actually solve this, I'm going to have to do the same thing where everything involving a j+1 is an unknown. So I'll have to take this equation and understand what the coefficients are and what the constants are. And this is the same thing then for the internal nodes and the internal nodes, and then that last one there is node n. Right. So there is a solution with the Crank-Nicholson technique here on the website. If you're interested in looking at it, you should be able to follow along with it and run it. And it's a like I said, it's a second order implicit technique, so it doesn't go unstable and it's relatively accurate. Okay, so the last thing we should talk about then are using ODE solvers that are available to you in software. And so the two that we'll talk about, because they're all kind of the same, is doing this in ease, and then also doing this in Matlab using the Matlab ODE solvers. So we'll do this in ease basically the same way that we did for the lumped capacitance problems, right? And that is that we will initially set the state variables. So in this case, we'll set all the temperatures and we'll set a value of time to some reasonable values, and we'll make sure then that we can calculate all of the temperature time rates of change using the state equations that we've come up with here, right? So where did my cursor go? So that'll implement these guys. We'll check the units. We'll make sure it all works okay. Actually, let's go ahead and look at that. I guess that's this one here. So I'll make this a little bigger. So here are all my inputs. This is just positions of the nodes. This is my initial temperatures, and then here I'm just setting some arbitrary values of the state variables in time, right? And that lets me make sure that I can calculate all these state equations. And as I said previously, these are state equations that are simple, but what's nice about this is any set of equations can be used as long as at the end of it you end up with d temperature d time. So we can look at these and we can check the units, we can make sure it all makes sense and everything like that. Once that part of the process is done, then what you want to do is comment out those arbitrary values of temperatures and time and use the integral command to integrate through time, right? So we're basically doing this operation, but for every single node, right? So temperature is my initial temperature plus the integral of d temperature d time with respect to time from 0 to my simulation time. And that becomes this equation right here, right? My initial temperature, my integrand is the first argument, that's d temperature d time. The integration variable is time the lower limit is 0, and the upper limit is tsim. And the only difference is that I got to do this for every single node, right? Not just for one node. So if I go back here, we would comment this out, and then we would put in the duplicate loop all of these calls to the integral function, right? And now if I hit solve, because I've set up an integral table somewhere here, this is time, and then this is the temperature of every single node at all times. And all the things we talked about before still hold. So for example, if I add an argument here, I can control the time step. If I put a colon here, I can control the times at which the solution is reported to me without controlling the time step. If I want to control the integration process, I have to go to this tab and change these values here, or I can use the directive that we had talked about before. But that's how that works. The last thing we should talk about then is, so let's see, using the ODE solvers in Matlab. So this is, again, sort of similar to doing this in ease, in that you have control of these state equations. So the first thing you have to do is write a function that takes in all the temperatures and time, right, and spits out to you all of these d-temperature, d-time values. So it's the same function we've already written, right? We wrote it for when we were doing the Crank-Nicholson, or I'm sorry, the Runge-Kutta fourth order technique. This takes in time and temperatures, and it gives me all these d-temperature, d-times. You can test that, make sure it's working. Once that's working, then you would call the ODE solvers, right? And it's the same thing as before. You have a first argument is just some indication of where the function is, right? What function do you want ODE 45 to use? You can give it a name if that function only takes in time and temperature, or you can map to time and temperature if it's a more complicated function. This is the range of times that you'd like to simulate. So we're going to go from 0 to tsim, and this is saying please spit back out to me every single time step you used. If I wanted to, I could put in a set of times in here, and it would only give me the answer at those values. This is now a vector of my initial temperatures, and this is that vector that I would set using the ODE set function that would allow me to control the integration parameter. And what I'll get back is all the times. For this particular call here, I'll get every single time step, and I'll get the temperature at every node and every time step. So this is now a big vector, a big matrix of temperatures at every node and every time step. So that's what I did here. ODE 45, lecture 19 is the function. This is the range of times. My T initial is just T infinity. I set the options here so that I have a smaller tolerance, and then I can plot the answer. And somewhere I have a plot, and it looks like all the other plots of that type have looked. So that's a whole bunch of different ways that you can solve this problem. Some of them are actually pretty sophisticated and pretty cool. They should be a pretty good tool set for you moving forward in terms of in terms of solving not only heat transfer problems, but really any problems where you have boiled it down to a set of state equations that you just need to integrate through time, right? You have now a bunch of options that you can use.